Hello, am I audible?
Yes, sir.
Uh, okay, good morning and welcome to lecture on advanced power electronics. We are meeting gap up after 1 week. Just we started the second topic and it is a multi-level inverter. In case of multi-level inverter, we are having three topologies. First topology is, you can just revise. First topology is dart clamped multi-level inverter, or it is called as a neutral point clamped inverter. Then second is a flying capacitor, and third is cascaded H bridge multi-level inverter. Out of that, we have discussed this first topology, neutral point clamped or the dart clamped multi-level inverter. This is a diagram we have discussed about a three-phase, three-level neutral point clamped inverter. Then we discuss what are its voltage levels, and voltage levels for three level inverter is VDC by 2, 0 and minus VDC by 2. Here is a concept we are calling as a complementary pair. So S1, so here S1 and S1 star will form one complementary pair. Similarly, S2 and S2 star will form a complementary pair. And we have seen that which switches should be on so that we'll get the voltage levels VDC by 2, 0 and the minus VDC by 2. Similarly, we have discussed the next, that is a 5-level neutral point clamped multi-level inverter. And again, we are having various switching states. And what should be the switching state when we obtain a VDC by 2, and for obtaining the VDC by 2, which switches should be on, which switches should be off. We are having 5 levels. A first level is plus VDC by 2, plus VDC by 4, 0, minus VDC by 4, and minus VDC by 2. Then after that, we have discussed the space vector diagram, particularly for, and we are done how to find out the space vector, particularly for a switching state we have discussed. And this is what we are having a space vector diagram for three-level neutral point clamped MLI. So basically we are having a hexagon. Hexagon will represent the space vector diagram for two-level inverter. And one side of the hexagon is VDC. For three-level, you divide the VDC into two, that is VDC by 2 and the VDC by 2. And then you join the lines parallel to the hexagon, join these points, lines parallel with the hexagon, you will get the space vector diagram for a three level. And here we have shown it here. So number of levels we are having is, so number of levels is particularly we are having a 27 for this three level multi-level inverter. Similarly, we are having a 5 level. So this is the space vector diagram for 5 level neutral point clamp MLI. And for 5 level, you divide the VDC into 4 parts: VDC by 4, VDC by 4, VDC by 4, and join the points, and you will get a number of switching states, particularly for this 5 level inverter, 5 raised 3. So it will be a 5 raised 3 level raised leg. With that, we are having a total 125 switching states. And this is the output voltage waveform, current waveform. Current is almost sinusoidal, RL low, and this is the phase voltage waveform, and the line voltage waveform we can obtain. And now after that, we have discussed the one switching method, or we can call as a PWM techniques for multi-level inverters, here used as a modulators. And here high switching frequency we have discussed is this a sinusoidal PWM. In case of high switching frequency PWM, there is a space vector PWM that we have discussed for two-level inverter. Similarly, it can be applied for multi-level inverter. Whereas this will be a switching frequency is high, maybe few kilohertz. In case of multi-level inverter, the switching frequency is few kilohertz. Whereas it is also possible high capacities, we can operate the switches at a low switching frequency, maybe a power frequency. And for that, we are having the two methods. A space vector control. Here we apply specific space vector, not the space vector PWM. So here switching frequency is low. One is very for a higher level multi-level inverter, we use a space vector control. Similarly, we can use a selective harmonic elimination. Specific harmonics we can eliminate, and for that we should have a specific switching pattern. Now today our interest is already we have discussed is a multiple carrier PWM, and here we have shown the one leg of three-level inverter, and we have shown it here. Particularly we are having four devices, we have two complementary pairs, so we require two switching signals. So here we require two switching signals, and for generating these two switching signals, we require two modulating wave. We require one modulating wave and the two carrier waves. So here, particularly for this case, we have shown it here carrier waves. We require two carrier waves. They are in phase, high frequency, maybe a 5 kilohertz or 10 kilohertz. We require these two carrier waves, and their magnitude is one carrier wave having a magnitude of 0 and 1. So one carrier wave is having a magnitude of 0 and 1. Other carrier wave is magnitude of 0 and -1. And we are having a modulating wave, that is for one leg we require one modulating wave, and its amplitude will vary from -1 to +1. And by controlling the amplitude, we can control the modulation index and we control the output voltage. So this is a particularly the carrier waves required for one leg. Same carrier wave we can use for other two legs. So carrier waves are the same, only modulating waves are phase shifted by 120 degrees. And so this is how we can go for a switching logic, particularly for one leg of the three-level inverter. And here we have seen that for one leg, this is one leg of the inverter, we require one modulating wave. So we require one modulating wave, and this modulating wave is given to a non-inverting terminal of the op-amp. Whereas for S1 and S1 star, we are having a carrier wave which is varying from 0 to 1, which is a high frequency of 5 kilohertz carrier wave, which is given to an inverting terminal. So comparison of this 0 to 1 and this modulating wave will get the switching of S1 and S1 star. Now for S2 and S2 star, we are having a modulating wave, same modulating wave, but carrier wave is having a 0 and -1. And comparison we can done with the help of this op-amp, and direct switching signal will be S2 and inverted will be a S2 star. So this is a switching logic, particularly for one leg of the inverter. Switching logic is for one leg of the inverter. Same we can have other two legs. Only difference is our modulating wave should be a phase shifted by 120 degrees for other two. Okay. So whatever three modulating waves, their phase difference should be 120 degrees. Now this is particularly for 5-level, how should be our multiple carriers. For 5-level neutral point clamp, we require 4 carrier waves because we are in 4 complementary pairs in the 5-level multi-level inverter. So we require 4 carrier waves. And these carrier waves are, one carrier wave is varying its magnitude from 0 to 1, other is from 1 to 2, third is 0 to -1, and -1 to -2. So we are having 4 carrier waves. These are also we can call as in phase. They don't have a phase shift. They are attaining the maximum value and the minimum value at the same time, and they are having a in phase four carrier waves. Their amplitudes we have just shown it here. And then our modulating wave maximum, when our modulation index is 1, we can say that the amplitude of the modulating wave is the 2. When our amplitude of modulating wave, sinusoidal modulating wave, is peak amplitude is 2, then we can say that the modulation index is 1. Now this is what we have shown it here, particularly MATLAB simulation. We have shown, we have generated the 4 carrier waves, which you'll see in a different color. Okay, one is from 0 to 1, then yellow is from 1 to 2, then green is from 0 to -1, and red is from -1 to -2. So these are the 4 carrier waves, and we are having a particularly the sinusoidal modulating wave, and comparison of these will be give a switching signal for one leg of the 5-level multi-level inverter. Then another leg, same 4 carrier waves, but modulating wave is phase shifted by 120 degrees. Now whenever we are having a 7-level, so whenever we are having a 7-level multi-level inverter, and whenever we are in 7-level multi-level inverter, we require 6 modulating waves. Sorry, we require 6 carrier waves. When we are in 7-level multi-level inverter, we require the 6 carrier waves, and these carrier waves are, one is 0 to 1, other is 1 and 1 to 2. Third amplitude is 2 to 3. Again 0 to -1, -1 to -2, -2 to -3. So this will be a, again we are having a 7-level. So in case of 7-level, we are having a particularly 6 complementary pairs. Okay, so that one leg contains the 12 devices, and total inverter will have a 36 devices. Now this is a, whenever we are having it is also possible, whenever we are having a it is also possible that our multi-level inverter levels may be even number. Multi-level inverters may have a even number, and we consider case of 8 level. When multi-level inverter is having a levels will be equal to 8, then here we have to get the symmetry, and for getting the symmetry, our first wave is starts from -0.5 to +0.5, not 0 to 1. If it is even is there, okay, even number of carrier waves are there, then it is okay, 0 to 1 and 1 to 2, like that. But whenever we are having a odd number of carrier waves, here we are having a 7 number of carrier waves, and as 7 number of carrier waves, it should be a symmetrical about the 0 or x-axis, and for that first carrier wave amplitude is -0.5 to +0.5. Then second is 0.5 to 1.5. Third is 1.5 to 2.5, and from 2.5 to 3.5. And similar for negative, -0.5 to -1.5, -1.5 to -2.5, -2.5 to -3.5. So this is the case for 8-level multi-level inverter. Similar this, okay, 6-level, again we are having the same, and here we have just shown the switching of the, which here whatever, whenever we are comparing with this, what will be a switching of the particular devices. So it will be we have shown it here. So this will be a switching of this, and whenever modulation index is high, we are just simulated a 5-level neutral point clamped inverter, and when modulation index is 1, this is our a particularly phase voltage waveform and the line voltage waveform. Okay, we are having a staircase type line voltage waveform, and definitely current is having almost sinusoidal. If you go on decreasing the modulation index, the nature of wave shape is going to change. Nature of wave shape is not remaining fixed. So when modulation index we decrease the modulation index to reduce the output voltage. So here it is a 1, output voltage is higher, fundamental component. Whenever we can go for zero point 0.8, definitely our output voltage will reduce, and there will be a change in the wave shape of the output voltage. Upper waveform is the phase voltage, and lower is the line voltage waveform. Similarly, if you go for modulation index 0.6, there will be correspondingly change in the waveforms, and then modulation index 0.4. The voltage levels are different here. Okay, so phase voltage peak value will be 100 volts, plus 100 minus 100, whereas is at 2 plus 200 and minus 200 in modulation index is a 0.4. If you just refer at modulation indexes, the phase voltage is plus 200, minus 200, line voltage is plus 300 and the minus 300. Okay, level. So levels will be changed. So this much we have covered last time. Okay, our last lecture we have just taken the review within the 15 minutes. Any questions? Hello, we have just discussed up till this now. Okay, before our test. Any question? Any doubts? Hello, am I audible? Any questions? Okay, let us start with now. Next, we start our lecture from here. Today's lecture, you can say it here, and our now our today's is how to generate the multiple carrier waves with the help of MATLAB simulation. So today we start with how to generate various carrier waves with different magnitudes and frequency. So we have to generate the carrier wave, and here whatever very simple logic is, we integrate the square wave to get the triangular wave. Very simple logic we have to use is, we have to integrate the square wave to generate the triangular wave. With that concept we are generating here. So just a block diagram we have shown. From MATLAB we can get a pulse generator with 50% duty. Okay, pulse we are having a 50% on time and a 50% off time. So we are getting the a pulse. So you are knowing the pulse is like something like this. I'll just have pulse will be 50% on time, let us assume, and 50% off. This is our pulse, and this period you can call as a let us call as a T. This period you can call as the T period. Okay, so this T period is nothing but, pulse period is nothing but, T period of the pulse generator is nothing but the pulse period or T period of the triangular wave. So carrier wave frequency will be determined by this T period. T period, from this T period will determine the carrier wave of frequency. So we select the pulse generator, and here pulse generator we have to select the amplitude, peak amplitude of pulse generator you can call as X. X is the peak amplitude of pulse generator. Okay, whatever this peak amplitude of pulse generator is X, and the period we can take, and duty ratio we take a, what is duty ratio for this pulse generator? D. Anybody, what should be the D we required? D will be equal to 0.5. Okay, because from the pulse we have to make the square wave. From this pulse we have to make the square wave, and for making the square wave we can subtract here. A pulse generator amplitude is X. Then from this we can subtract X by 2. So a constant will be our X by 2. Constant will be the X by 2. So here pulse generator we are having amplitude of X. Pulse generator we are having a amplitude of X. X is the amplitude of a pulse, 50% duty cycle. and t is the period of the pulse, and that will be the same as the 1 by t, that will be frequency of the carrier wave. And from this pulse we want to have a square wave of amplitude x by 2, and for getting this pulse generator, from this pulse generator we subtract a constant x by 2. Then here you will get the square wave of x by 2. So here we obtain the square wave of x by 2. Here we can get the waveform of the square wave. And this is square wave, is amplitude is x by 2, a square wave we are having. So this will be our square wave. We obtain this amplitude is x by 2 and t period is whatever we are having, same as that of a pulse generator. And once we get this here, this we can obtain at this position a square wave which is having an amplitude x by 2 and period equal to t. This just integrate to get the triangular wave. And depending upon what is the initial conditions, from that whether at the B point we'll get a 0 to 1 or -1 to +1. Okay, so here we let us assume that with the initial condition as a 0, we'll get a here having an amplitude will be equal to 0 to 1. At B, point B, we get the amplitude will be 0 to 1. In that we add 1. Whatever we add 1. So here at we'll get the amplitude variation will be 1 to 2, a triangular wave, but variation will be 1 to 2. Then from 0 to 1 wave we subtract it -1. So it will be a 0 to -1 you will get. Okay, and then D we are getting a -1 to -1. So this is a very simple logic. We generate the multiple carrier PWM. So let us go how to find out the values for X. That is value for X depending upon the particular frequency. So we are already discussed that t period we are having. This is whatever blue is the pulse we are having, and its period is the t. Whatever required frequency, a 10 kilohertz. Let us take the 10 kilohertz. For 10 kilohertz, what should be a t? For 10 kilohertz, 1 by f, the t will be a 100 microseconds. So this period will be the 100 microseconds. Amplitude, we are in general case, we have taken as a x amplitude, and duty ratio is a 50%. So this period is t by 2. Now from the x, this pulse, we subtract the x by 2 constant, and if you from x, this pulse, if you subtract the x by 2, then we'll get the square wave of plus x by 2 the minus x by 2. We'll get the square wave. Okay, so we get the square wave, and this square wave we integrate with the help of integrator with the initial condition as 0. With initial condition as 0. And once here we start, initial condition is 0, integrator it will go to the 1. So if you are in x by 2 into t by 2, that will be equal to 1. X by 2, we are going to integrate x by 2 into t by 2. Okay, magnitude, this integration is nothing but area under curve. So t by 2 into x by 2. So we just get this equal to 1. T by 2 into x by 2 will be equal to 1. So once we know the 1 is known, and we are having what frequency we have to generate the carrier wave, that is known, P is known, and from that we can get the amplitude of X. Let us assume that for 100 kilohertz, sorry, for 10 kilohertz, we want to generate a triangular wave having a 0 to 1. And in that case, if we just put here t equal to 100 microseconds, and then value of x, you will get a 40,000. This is the one case where integrator initial condition will be 0, and so that will get the triangular wave from 0 to 1. Yeah, this will be a triangular wave we can get. And so this is what available at B. This is how we get integration of this. And just otherwise, now simply you add one or the subtract one, like that you can just generate the other waves. Okay, so in that case, if you 0 to 1 is there, you add 1, it will become 1 to 2. 0 to 1, you subtract 1, it will become as a 0 to minus 1. And then here from this again you subtract minus 1 to the minus 1 and the minus 2. So this fashion we can obtain the carrier waves, particularly for whenever or odd multiple is there. Okay, we are having a 5 level, 3 level, 7 level multi-level inverter. We can use this strategy. Now another case, if you want to have a carrier wave which will be vary from minus 1 to plus 1, minus 1 to the plus 1. So here we have shown this another diagram where our carrier wave is not varying 0 to 1, but here it is varying from minus 1 to plus 1. Minus same, we are having a pulse of t period, amplitude will be x. Now we minus subtract x by 2 from the pulse, so we'll get a square wave of plus x by 2 and the minus x by 2. But here we have to put the initial conditions of integrator initial conditions as the minus 1. So we start from minus 1, we reach to 1. And so our expression for finding out value of x, t by 2 into x by 2 will be now becomes equal to 2. Okay. And from that 10 kilos, you have seen that for 100 microsecond, if you want to have a 0 to 1 carrier wave, our x value is 40,000. Now we want the carrier wave which amplitude should vary from minus 1 to plus 1, which amplitude should vary from minus 1 to plus 1. Then our x should vary to a 80,000. X will be vary to a 80,000. Now once we get this, okay, once we get, and then how we can develop the logic for 5-level diode clamped MLI. This is the way I've shown the one leg for diode clamped MLI. So totally we are having 4 complementary pairs. We are in 4 complementary pairs, S1 and S1 star, S2 and S2 star, S3 and S3 star, S4 and S4 star. So we have to 4 complementary pair, means we have to generate the 4 switching signals. So we have to generate the 4 switching signals, and for that we require 4 carrier waves. So first carrier wave is varying from 1 to 2. We have just now discussed how to generate the carrier wave from 1 to 2, how to generate carrier from 0 to 1, 0 to minus 1, minus 1 to minus. And we require to make a 4 comparisons. Okay, here we shown for op-amp, we have shown it here. This is one leg, so that we are having a modulating wave. And we have shown it here, modulating wave is given to a non-inverting terminal of 4 op-amps, same modulating wave. It is one modulating wave for one leg, another modulating wave for another leg, and third modulating wave for third leg. And these 3 modulating waves should have a phase shift of 120 degrees. And now here we are making a comparison of carrier wave 1 to 2 and the modulating wave, and the signal will go to a upper device, first upper device SA1, and inverter will go to a lower side of this SA1 S1 star. Now second comparison is carrier wave is 0 to 1, and it is compared with again same modulating wave, and direct comparison will go to a S2, inverted will go to a S2 dash. Similarly, for third device, our carrier wave is 0 to minus 1. It is compared with same modulating wave, and signal is given to a third S3 and S3 star. Here we add A is for A leg or first leg. Similarly, for finally, we are having carrier wave minus 1, minus 2 variation, and compared with the modulating wave to get the switching signal for S4 and S4 dash. So this is for one leg. Similarly, you can go for the second leg and the third leg. So this is how we generate the sinusoidal PWM, and for that how we generate the multiple carrier PWM. So any question? How to generate the multiple carrier PWM? Am I audible? This is one logic we have presented here. You can develop any logic, different logic. So any question on this? Multiple carrier based PWM, how to generate the multiple carrier with different amplitudes. Hello, am I audible? Hello.
Yes, sir. Yes, sir.
So,
Audible.
any questions? Any? Okay.
No,
So
sir.
how to generate the multiple carriers, triangular wave carriers with the help of MATLAB simulation that we have discussed, and how to select the pulse amplitude and the pulse frequency or pulse period t, so that we can generate the required frequency and required amplitude triangular carrier wave. Any question? Okay, so this will be one sinusoidal PWM, multiple carrier sinusoidal PWM. Now let us go for a space vector PWM. How we use the space vector PWM for three-level multi-level inverter. A three-level multi-level inverter. Now if you see here, we have drawn the space vector diagram for three-level diode multi-level inverter. Okay, and we have shown it here. We are having a triangles. Okay, and each vertex of the triangle is represented with a specific switching state. Each this corner of the triangle we are having a switching state of this. And here we have to consider three magnitudes of space vector and particular location. We have seen that space vector is continuously rotating. A space vector is rotating at some angular speed. Some angular speed depending upon the frequency. Here we have shown three space vectors. A red, which is having a higher magnitude, then slightly reduced, we are having a blue space vector, and third is the yellow. We have shown different magnitudes of space vector, and they are lying in different triangles. They are lying in the different triangles. Let us consider this space vector at one particular position. Okay, and its tip lies in the red. We have just shown it here, a red triangle. We just shown it a red triangle. Its tip of this particular lies in the red triangle, and here we have shown that. So which switching states we can apply for this? Which switching states we can apply whenever our space vector is red and it is in the given position? So we have to apply in that triangle. We are having a upper these two switching states. So this is the AOB and ABB. These two switching states we can apply. Calculations we can do a similar to calculations can be done similar to a whatever we have done the space vector PWM for a two-level inverter. So here what switching states we can take? This is one switching we can take. This one switching, these two active. This theta is known, and at origin we are having a 3. This 3 plus this 2. With the help of that, we can make the switching signal generation. So always we can use the two active switching states, and we can use 3 null states or 2 null states or 1 null test, whatever this depending upon requirement. So for 3-level space vector diagram, whenever space vector is in this particular sector, we can use this particular. Now second, so here we have to use these two active states. For this red space vector position, we get one switching state is AOB, other is ABB, and we get the null vectors at 0, 0, 0, AAA or BBB. Out of that, we can construct the space vector. Now let us assume that consider second case here. This is the blue space vector. And here for this case, we have seen that the triangle is having three, okay, active states. But now out of that, because it is coming towards this in the other half of the triangle, so definitely we can use the AOB and this AAO or OOB switching states and the switching state at origin. These three plus these two we can use. This may be a second case. And now third case, when space vector magnitude is very low, we have seen it here, a yellow particular triangle. In that case, we can use two the switching states and the origin switching states or null switching states we can use to construct this. So space vector, particularly for 3-level, will be on the similar lines whatever we have discussed for the 2-level inverter. And here we have shown it three cases how to which a particular space vector we can take for generating the switching signal for this 3-level multi-level inverter. So any question on this? So where tip of the space vector, which triangle's tip of the space vector lies, on that particular triangle we can take a two switching states. Okay, here we are having these two switching states. If it is lying it here, then we have to use these two switching states. So for each space vector, we have to take a two active switching states. Now here, if we are shown the space vector diagram for 5-level MLI. So in case of 5-level MLI, this is our VDC. This VDC you are divided into a 4, VDC by 4, VDC by 4, VDC by 4, and VDC by 4. Divide into 4. Get the each side you divide into 4, and then join with the parallel lines to the sides of the hexagon. Then you will get the so many triangles in that. Whereas here we have shown one space vector, V star we have shown, and in which sector it is lying, we have shown it here. Out of that, we can use the two switching states of this, and the switching states at origin we can use particularly to construct the switching signal to generate the V star. Okay, so this will be a space vector PWM which we are having a higher switching frequency, maybe 10 kilohertz or 5 kilohertz. Now let us take this particular, see the space vector diagram. Now this is a space vector diagram. If you see it here, okay, this is a VDC, and this VDC is divided into 10. This VDC is divided into the 10 parts. This VDC is divided into 10 parts. Okay, VDC is divided into 10 parts. And so whenever this VDC is divided into 10 parts, what is the number of levels for this multi-level inverter? When this VDC is divided into 10 equal parts, then what is number of levels for this inverter space vector? This VDC is divided into 10 equal parts. So what will be a level of this inverter to which the space vector belongs? Hello? Hello, am I audible?
Yes, sir.
Now VDC we are divided into 10 parts. VDC length, this is a VDC length, we divide into 10 parts. Then what is the number of levels for the inverter?
11.
11 levels. So this is our inverter is a 11 level inverter. Okay, we are having a 11 level inverter. And whenever we are having 11 level inverter, and we have shown the circle, okay, from this is our space vector. Okay, this is the space vector magnitude, we want it. Then here, if you see that number of levels are there, then you see the thick states, switching states. So we apply only these fixed switching states. This particular switching states we can apply particular duration. Okay, so we are not going for a PWM. We are going for switching at a specific step or specific state we apply for a particular duration, and then we get the space vector. And that technique you can call as a space vector control, not the space vector PWM. Here we are applying only a specific switching states we apply. Suppose we want a lower voltage, then we can apply the here switching states of the inner side, whatever we are. If this is circle, I am not able to draw it circle correctly. Okay, so this will be a inner switching states we can apply to get the lower voltage. Outer switching states we can apply to get a higher. Similarly in the middle. So here in this particular a technique, we are applying a very specific switching states of the inverter, and we are not going to divide into a PWM. So here a specific switching state is applied, and for this particular circle, the circle will represent a magnitude of the space vector. This is what we are having at from the center. This will be the magnitude of the space vector, and if you want to this magnitude of space vector, then we apply. These are the switching states which we have shown with a okay a bold case. Okay, the switching states we have shown with a bold, and from that, okay, these switching states which are shown with bold we can apply, and based on that we'll get the output voltage, and that technique we can call as a space vector control. And the space vector control is a switching at low frequency. Particularly here switching frequency is low, we can call it switching frequency is low, or power frequency you can call it. Switching frequency of that will be equal to a power frequency. I will not power frequency, I will call it a power frequency. Okay, so that will be the technique where we can call it as a space vector control, not the space vector PWM. So there is a difference. So here what we are discussing is space vector PWM, and here this method we can call as a space vector control. In case of space vector control, switching frequency is low, and this may be applicable to whenever we are having inverter is having a with a high number of levels, and we presented a case here for 11 level MLI, and for that case we are not going for a space vector PWM, but we are having a space vector control. A very specific space vectors we can apply. Direct we apply the space vectors for a particular duration, and based on that we'll get the output, and because of that our switching frequency is less, so power loss in the device will be reduced. So this will be what we are discussed about. This will be a particularly one topology of a multi-level inverter, and that topology is we call as a neutral point clamped NPC or diode clamped multi-level inverter. Today now we are going to discuss this. Now we start the second, that will be our flying capacitor MLI. Another second, that will be a flying capacitor multi-level inverter, and again we are going for 3 level. First we can go for a 3 level flying capacitor MLI, and now here, so in case of 3 levels, as you know, these are the levels VAO, where this is O is the center point of our DC, and A is the output of the leg. You are knowing we are using the capacitors C2 here. Okay, so we use the two capacitors. So here we are using the C2 and C1. These two C2 we are using equal magnitude. So to divide the DC link voltage, so voltage across each capacitor. Here you can say it here, voltage across. Here we are not using diodes. Okay, in that case we are using the diodes in case of first topology. That's why it is called as a diode clamped MLI. Now here we are not using the clamping diodes. Here we are using the capacitors, and they are connected between the devices, flying. So we can call as a flying capacitor. So here in this topology we are using the flying capacitors, or we are using the capacitors only. Now this C2 capacitor we are having the two capacitors, and purpose of this is to divide the DC link into VDC by 2 and the VDC by 2. That is the purpose. So we get the point O, and this is our A. And here, particularly for 3 level, VDC by 2 means A is point is connected to the upper this. So this A point, whatever this A point is connected to add this point here. And for this case, we have to require to be on. Our S1 and S2 are on. So S1 and S2 is on. Then how will current will flow? When S1 and S2 is on, our current will flow from capacitor this through S1, S2 through this, and from this load it will come at the up this. So load is connected between this. So C2, whenever S1, S2 is on, and we get a load voltage will be VDC by 2, and here C2 will be a upper C2, that capacitor will come across this, and voltage applied will be a VDC by 2. So here S1, S2 is on, upper 2 are on, lower 2 are off. So S1 star and S2 star. S1 star and S2 star, these two devices are off. Now if you want to get the second VDC minus VDC by 2, so our S1 star and S2 star are on, and so this A point will be connected to a minus VDC, so we'll get the VDC. Whereas when we get a 0, particularly when you get a 0, then S1 and S1 star are on. So this is a, here we don't have a, so whenever S1 and S1 star is on, how we get a 0 voltage? So let us assume that it's a blue, S1 star is on, S1 is on, sorry, S1, then S1 star is through this and this. So each capacitor C2 and C1, now they will, C2 is having upper positive, lower negative. Similarly, C1 is upper positive and lower negative. These two capacitors will come in series. These two capacitors that will be a C2 and C1 will come, but they are in opposition. They are having, each capacitor is having a voltage will be equal to VDC by 2. So this VDC by 2 across the C2 and this plus VDC by 2 across the C1, they are coming series opposition, and so that these two capacitor voltages will be neutralized and output voltage will be 0. This is a when S1 and S1 star is on, when S1 and S1 star is on. Another switching state we are having, in that case our S2 and S2 star is on. So here S2 is on and S2 star is on. So how? So we can have from this side S2 is on, from S2 then capacitor, and again this we are having like this. And in that case we have seen that this lower capacitor and this capacitor will again come in series opposition, and then output voltage will be 0. So how it will be a different from diode clamped MLI? In case of diode clamped MLI, there is a concept of complementary pairs. Here no concept of complementary pairs. S1 and S1 star, if you see here, S1 and S1 star are on simultaneously, S2 and S2 star are on. So no concept of complementary pair is here in case of a flying capacitor. Here just capacitor voltages, we are making it proper additions or subtractions so that we'll get the levels. That is the meaning of this. So whenever want to 0, when we get a 0, these two capacitors, this capacitor and this capacitor opposing each other, and each is having a value equal to VDC by 2, VDC by 2, and so that the output voltage will be a 0. So here this particular, so no concept of complementary pair, and it is possible that 0 we are having a 2. If you want to have a 0 VAO level, then we are having a two possible options. Two possible options. So this is the case. Now we have shown it here. Particularly, this will be a 3 phase, 3 level, diode clamped, three-phase, three-level flying capacitor, multi-level inverter. So this is one leg, a second leg, and the third leg. So here we require these three capacitors, one capacitor per leg, and four devices per leg. And we have seen the switching logic here. Okay, so that we can use it here. So this is a three-level flying capacitor MLI. And now next time, okay, we are going for the a five level of flying capacitor MLI. Okay, we'll discuss more details about the five level. So any questions, whatever we discussed today? Any doubts, any questions? Hello? Any question? Okay, so tomorrow we'll
No,
meet at same time. Any question? Yes?
no, sir.
Okay, so we'll meet tomorrow 11:15. Sorry, 10:15 a.m. And after that, 1:30 we are having a particular test for our lab assessment. Okay, so thank you. So we'll join tomorrow at 10:15. Thank you.
Okay, sir.